Well, good morning, Chemistry 20s. Today we are talking about polarity, and we're going to ask the question for some molecules. Is it polar or not? So I have to know our VSEPR structures for this. And so remember, table 7 on our VSEPR notes guide has our molecular shapes. So here's what we have to do. Every single time you're asked to determine polarity. Number one, you look at the electronegativity difference between the atoms. If it's between 0 and 0.5, we consider it a non-polar molecule. So remember, this is a continuum that we're looking at. Between 0.5 and 1.7, we say polar. Between 1.7 and 3.3, we say ionic. So don't forget, some molecules that are actually covalent, they're non-metal, may have a really high electronegativity difference, and they behave like an ionic compound. The second thing you have to do every time you're asked if a molecule is polar or not is you draw out the molecule. You draw out the VSEPR shape. You decide, is that molecule symmetrical or not? So here's some examples for you. Our first example, CO2. This is a linear molecule. I've got for you the structural formula, the Lewis dot formula. Remember that when you're looking at that central atom, carbon, each of the double bonds is going to count as one bonding pair. So it has two bonding pairs, 0 lone pairs, and 2 total pairs. So this is our molecule, and you can see that it is linear. Carbon is the black atom in the center, and there are two oxygen atoms and a double bond between each. So that is a linear molecule. So how do we decide, is it polar or not? Draw it out. So then you look at the electronegativity difference between atoms, and you see that between each carbon and oxygen is a difference of 0.6. So that puts us into this range, right? The polar range, 0.5 to 1.7. But here's the deal. Even though it has bond dipoles, it is a symmetrical molecule. The dipoles cancel out, and so this means that the molecule is non-polar. Let's do another couple of linear examples. I've got 2 for you on this page, hydrogen chloride and hydrogen gas. And so I have the molecules for you. I have the molecule HCl, whoops, there he goes, HCl, and just plain hydrogen as this molecule. H is the white atom, and the green atom is chlorine. Here there's 2 hydrogen atoms. So this is linear. These are both diatomic. There are 2 atoms, but the HCl is going to be polar. The hydrogen is not. Why is that? Because the HCl has a polar bond, has a dipole, and it is not symmetrical. 2 different atoms makes it a polar molecule. Compared to hydrogen, no electronegativity difference. It is symmetrical. That is a non-polar molecule. Okay, here's my next example for you. Bent, angular, V-shaped. Water is our first example. There's our Lewis diagram, our structural diagram, and then you can see it is definitely a V-shaped molecule. Here he is here, H2O. Obviously, the oxygen is the red, and then the 2 hydrogens are the white atoms. So this is not a symmetrical molecule. It is polar. It has a net vector. You look at the bond dipoles, and there is a difference between the hydrogen and the oxygen atoms that put them into the polar range. So there are polar bonds, and because it is not symmetrical, it is a polar molecule. Now, I couldn't build this one, but sulfur dioxide is another polar molecule. It is another V-shaped molecule, but it has a central atom with 2 bonding pairs and 1 lone pair for a total of 3 total pairs. So that is different. There's 2 different ways that you can get a bent or an angular or V-shaped molecule. Okay, next we're moving on to tetrahedral. So our example is methane. And so we've got our structural diagram, our Lewis diagram, and we can see that this molecule is tetrahedral. Has 4 bonding pairs, 0 lone pairs, and 4 total pairs. How do I know if it's polar or not? You draw out your stereochemical diagram. You look at the bond differences, right? The electronegativity difference between the hydrogen and the carbon is 0.4. That falls into the non-polar range. There are no dipoles. Plus, it is a symmetrical molecule, so that makes it nonpolar. Now, what if I went and I changed and I put this atom on top instead? This is a chlorine. So now what do we have? Well, if we do that, now if we have a chlorine atom on top instead, here's the deal. There is a dipole, and this is no longer a symmetrical molecule, and therefore it becomes polar. Okay? Trigonal planar. I had to make this one up. I didn't have the actual molecule. So here's our example, boron trifluoride. Now this guy is, boron is an atom that violates the octet rule. So we've got our Lewis diagram, 3 base bonding pairs, 0 lone pairs, total of 3 pairs. And this makes it trigonal planar. So you can see this molecule, and I'm sorry, it's not the greatest molecule, but it's going to work for us, is all in one plane, right? There is no atom sticking out at you or away from you. It's all in one dimension. I want you to compare that to our trigonal pyramidal. It's a pyramid, right? If you look at it, there's one atom sticking towards you, one away from you, into the table below me, and then the atom that is at the same angle in the same plane. So this is our example of ammonia. And ammonia, as we can see, has one lone pair on top. And so that's this little hole here is indicating that there is a lone pair. 3 bonding pairs, 1 to each of the hydrogens. So it is pyramidal, and it is a pyramid, right? Not in one plane, not planar. So again, when we're looking at polarity, when we are looking at any pyramidal molecule, any trigonal pyramidal, they're always going to be polar. Why? Because they have that huge lone pair of electrons. We typically don't draw out that lone pair when we're doing our stereochemical formulas, but we have polar bonds. We have a not symmetrical molecule that is polar. Now, just as a reminder, do not mix up ammonia. Here's ammonia, NH3, that's the molecule, it's pyramidal, with the molecule ammonium. Now ammonium, look, I just made ammonium. What did I do? I added a hydrogen on top, and now it has an extra H plus, and that's why it has a positive charge. So now if you look at the shape, guess what, guys? That's tetrahedral. So that molecule and our methane molecule, now you can see that they are exactly the same. Okay, they are symmetrical and they are tetrahedral. Okay, so remember, ammonia didn't have that extra hydrogen at the top. It's trigonal pyramidal. Ammonium, on the other hand, is just like methane. That is going to make it a tetrahedral AX4. All right, that's all I got for now. Hopefully you guys are able to do your questions. This helps out. As always, Michelle.Ladine at ghsd75.ca. Take care.